Hello, good morning, everyone. This is Francesco Malandrino, your favorite influencer from CNR, Italy. And I will be talking to you about distributed learning in edge scenarios. Let us start with some background about learning and parallelism. It is almost a truism these days to mention that machine learning is everywhere, artificial intelligence, which is the same, is also everywhere, and in particular within networks, we see them both at the network management layer, in the sense that we use machine learning to manage the network at different layers, from the radio to the orchestration. And also a lot of the computation we perform within the network is also machine learning. Most of the verticals in edge computing scenarios, they perform machine learning. And when we say machine learning, a lot of times we say deep neural network. They are made of different layers. Layers are made of neurons, and they 99% of the examples, they transform pictures into classification decisions. Now, this DNN works very well. However, training them is a complicated process. It requires calculating gradients, moving them back and forth. And this is a problem. It becomes even a more significant problem when we think that there is a trend going on towards larger, wider, deeper neural networks. In this context, distributed learning seems like a very attractive idea. Now we have multiple nodes and they can cooperate in a learning task, which means that we can use more data without having to actually transfer that. In many cases, you don't really want to move data around. It can be a privacy problem. It can be belong to somewhere that they don't want that to be moved, not to mention overhead. And also we can have more computational power at our disposal by taking the power of multiple nodes, as opposed to buying one huge, powerful hardware, which is probably also very expensive. Now, there is no free meal, and in the case of distributed learning, the concerns include network overhead. It may be longer than the time gain that you get from the more power or the more data. And also, convergence may be slower because you have to wait for the slowest node. So it's not always the case that you want all the distributed learning you can perform. And one of the first decisions that you want to make when doing distributed machine learning deals with parallelism. So there are two ways, essentially, to exploit multiple nodes. The first one is data parallelism, data. So you have data in multiple nodes. Each of these nodes run the full DNN. So here we have the same layers that we were seeing earlier. And then at some point you average these models. Remember, models are collections of matrices, so the simplest thing in the world is to average them. And this is the basic idea of the federated learning and its variants. Federated learning is very popular. There are many tweaks about that, but the idea is different nodes have different copies of the same model, and then you combine these copies. The opposite, if you like, dual, is what they call model parallelism. So in this case, there is one model, one copy for each layer, and different layers, different parts of the model run at different nodes. In this case, you don't necessarily have data around the network, but you have a lot of computational capability and you want to exploit as much as possible of that. And one of the most typical, one of the best known strategies doing that is what they call split learning. And usually in the literature, you find proposal to achieve one of these two main approaches. In edge and fog scenarios, become a little bit more complicated because on the one hand, you have user devices, cars here, cell phones, of course, which have data. But then you also have edge nodes, which have computational power. So in this case, do you want model parallelism or data parallelism? And the answer is that you want both, and that becomes even more complicated, even more interesting. That is, in fog scenarios where some devices have both computational capability and they generate data. So the idea is the traditional, the classical dichotomy between data parallelism and model parallelism is not adequate to this scenario anymore, which is why we are proposing something else, something that we call flexible parallel learning. The basic idea is because edge scenarios are so complicated that they require both data and model parallelism, well, then we use them all, and more precisely, we mix and match them in order to suit the scenario that we have to deal with. And what we do, for example, in this very simple case, we have two cameras looking at the same object, the same tree. So what you do, for the earlier layers, the layers closest to the data, you duplicate them as if you had data parallelism. And then for the later layers, you can start merging them as if you had model parallelism. So the idea is that in FPL, in flexible parallel learning, the DNN structure is not a sequence, it is not a chain of layers anymore. It starts looking like a tree with the leaves being, well, close to the leaves of the tree. So at the beginning, at the data sources, and the root being the last layer, the one that eventually gets the answer, this y hat. And the idea is we can freely build this tree in such a way to match the network topology of the edge scenario, which again is more or less a tree with many devices, then a smaller number of edge networks, and then there is the cloud at the top. You have, however, to perform one additional change to the network, and that is to add what we call a junction layer. Now, the junction layer is an additional fully connected layer which we add to the DNN, to the neural network, whenever two branches join, in this case here. So we have two branches incoming, so two copies, if you like, of layer C2, and then we have one copy of layer F1 running somewhere else, and so we need to somehow combine the outputs of C2A and C2B into the input of F1. So the junction layer, which is the most important thing that we want to remember about FPL, has two functions. First, like we said, it matches the input and the output. So in the original, in the chain-like neural network, the output of C2 and the input of F1 are the same. Now we have two copies of C2, and they cannot directly fit inside F1. We need to adapt that, and this is one of the functions of the junction layer. The second and most important function is what if the data coming from the green the green photos are of better quality than the orange photos? What if they are of better resolution, or they represent more objects? What if essentially the output of C2A is better, is closer to the optimum than C2B? Well, then you want to give a higher weight to this data here, to the data coming from C2A compared to the data coming from C2B. And this is one of the things that the junction layer will do for you for free. So it is a layer, it is a DNN layer, just like F1. So when you train the network that you have built, thanks to FPL, and you can train that using any state-of-the-art algorithm for free, you also get these parameters which tell you which of these data sources is better and what is the optimal weights that you give to them. And make no mistake, this is a very important thing, because usually data quality is a separate problem. You have a whole research trend trying to estimate the data quality of different sources. For example, you look at entropy in many cases, and then you try to integrate knowledge about the data quality into your decision making. And so we are getting all of this for free thanks to this junction layer. Now, you probably have noticed that there is no free meal. So junction layer has costs. First of all, it is one more layer in your network, so the training will be longer. Also, this is a fully connected layer, so they have many parameters, so the network size will be larger, and there will be more data to send back and forth to the net to train the network. So in general, learning becomes more complex. This is this issue, this effect is more significant when you are putting the junction layer early in the DNN structure. So you know that the size of data gets lower when you move from the input towards the output of the DNN. So if you put the junction layer very early in the network, you are dealing with very large inputs here, which creates a very large layer. So the point is, junction layer will do amazing things for you, but we need to be careful when designing an FPL, a parallel, flexibly parallel DNN. So there are two main things. On the one hand, we want to carefully place the junction layer, and if need be, we will have to prove it. And this is what we are going to see next. So like we say, the problem is that the junction layer is potentially large and fully connected. So one thing that we can do about that is to make sure that the layer is not too large. And the best way of doing that is, insofar as possible, to place it late in the DNN structure when we have traversed, for example, the max pooling layers, which decrease the size of the output. So if we place the junction late in the DNN structure, then the input and output will be smaller, so the number of parameters will also be smaller. As you remember, the number of parameters of a fully connected layer is proportional to the product between input and output dimension, so it's a quadratical dependency. The other thing you can do, and this you can do if for some reason you have to place the layer at the beginning of the DNN. So in that case, you should not despair, but you should think about pruning that. So like we said, a normal fully connected layer has a square number, no, sorry, it has one parameter for every input-output pair. Now the question is, do I need all of this? So if I have one copy of the input here, make it 100 byte, and then I have the same corresponding 100 byte here. Remember the drawing earlier with the two copies of the same layer. So am I willing to combine the 19-second bit here and the 49th bit there? Probably not. I mean, in most cases, I'm going to combine corresponding bytes of the inputs. So why not pruning? Why not removing from the junction layer, in theory, all parameters that are not connecting, are not dealing with corresponding bytes? And then I'm only learning how to combine the first byte of the first input with the first byte of the second input, and the second byte here and second byte there, and so on. In this case, I'm still learning the quality of different outputs, but I'm not wasting space by considering all possible, very unlikely and very strange combinations between the two, but only the natural ones. And as we will see now, combining these two techniques, we can have a very interesting performance. So the reference scenario that we consider takes very standard, very common DNN and dataset, so that the results we come up with are more significant and also easier to reproduce if you so choose. So the DNN is actually a very simple one. It's a convolutional network for image classification. So there are two convolutional layers. They are followed by a max pooling layer and then two fully connected layers. A fairly common structure, actually. The dataset is MNIST. So it is a variant of the more famous NIST, which is the one with the digits. So this is enhanced in the sense that there are lowercase letters, uppercase letters, and digits. So it's a little bit more difficult to learn from. And we consider 5 network nodes, 5 sources. Now, if you remember the examples, 5 cameras, each of these cameras corrupts, if you like, alters the images in one of these 5 different ways. So you can blur them, you can erase, you can flip horizontally, flip vertical, and here it is just a zoomed version. So you have different data quality, just like in our scenario, simulated by altering the input images. So performance, we compare FPL with the 2 main alternatives, which are federated learning and split learning. And for FPL, we consider different places where we could put the junction layer. And what we see, you have the full results in the paper, of course, but what we can see is that in general, FPL outperforms alternatives. So at every epoch, the validation loss is lower. And also, if you look at the markers represent the minimum of the validation loss. So this traditionally, machine learning 101 is the point where you have finished training and you start overfitting. So when you get to this marker, it means that your training is finished. And this moment happens, as you see, earlier for FPL than for its alternatives. So this is an important point. FPL not only gets a better learning performance, but also learning is shorter, takes a smaller number of epochs. This is very important when we move towards overhead. So this is the bad news. This is the number of parameters. Green is FPL. So we have more parameters than the others. Like we said, there is the junction layer. It is a potentially big layer. So it is costing us some extra parameters. However, when you move at the training time, well, FPL is shorter than the other ones. How is that possible? We perform a smaller number of epochs. And similarly, for the same reason, because we are doing less epochs, we also have a smaller network overhead. So, sorry. So we have larger networks, but we are sending around smaller quantity of data because we are doing that less frequently. And it's also important when we start thinking about energy. So it is a European call time. So you all know they are about 2 things. They are about machine learning and they are about sustainability. However, they are one of the opposite of the other. Essentially, training neural network is very expensive. And in this context, FPL can help, as we can see here, both in the energy and equivalently the CO2 that we produce. It allows to have good trade-offs between energy and learning performance, essentially because it can reach convergence in a smaller number of epochs, so it has better performance than split learning and lower energy cost than federated learning. So it allows us to explore more solutions and potentially more interesting solutions when we are moving across this, let's say, space, considering both energy and learning quality. So it's time to conclude, and I will just say that we have introduced something called flexible parallel learning, which allows essentially to adapt the DNN structure to the network structure in edge scenarios. The main tool that we use is this purple junction layer. by so doing, the junction layer is able to connect different branches of the network and also account for the quality of the data coming from these branches. It's very important to decide where to place this network and also, this layer, and also how to dimension that, how to prune that. And this is what we are currently working on.